Let's look at the API for read copy update. So for readers, we have 3 calls. We have RCU ReadLock and RCU ReadUnlock. So these are going to be defining a critical section. And then RCU dereference, that takes a pointer that may have been set by another CPU and dereferences it. The read and write barriers are why we're going to actually use a macro for this. And then for updaters, we have synchronize RCU and RCU assign pointer. So RCU assign pointer is going to be used basically to assign a pointer that may be seen over by a reader. Again, this gives us an opportunity to go ahead and do any write barrier that we need to make sure that we have successfully done any previous writing, such that once this pointer is set, the reader can go ahead and use RCU dereference, set up a read barrier if necessary, and then safely use this dereferenced pointer, knowing that all the values have been set appropriately. So how does this work? Well, this is the read side critical section, right? So the rules are, 1, no blocking. So reader can't block during its critical section. And another rule is that the reader can only have access to the RCU protected data structure during its critical section. Okay, so within RCU ReadLock and RCU ReadUnlock, it can go ahead and dereference any pointers into the data structure and use that data structure. And then a third is the reader uses RCU dereference to deref pointers in the data structure. Given that, we know that pointed to objects will exist throughout this critical section. But as we saw in the introduction, we don't know whether it's going to be old or new. So that's part of what we have yet to determine. So how it basically looks is something like, right, you'll do an RCU ReadLock. This is a reader, of course. And then within here, you'll do some, you might say P equals some RCU dereference of a pointer into the data structure. And then go ahead and do something with P. And you're guaranteed that this lifetime of this is going to exist while you're in this critical section. And then finally. So as an example of what this might be, let's say that you've got a linked list and you've got an updater who's deleting an object. Well, it may be you get a read lock and then you dereference and get that object that the updater is trying to delete. You're guaranteed that that object will continue to be valid throughout this lifetime. So you have no concern that the updater is going to somehow free the object out from under you. You're guaranteed that that's okay. So how does it work for updaters? Well, here are your rules. So one is you can make changes at will as long as they're not going to be seen by readers. Do we have an example of this? Sure. In the linked list, when we were doing an insert, we went ahead and malloced a new node and filled in fields in the node, including the next field. That's okay, because no readers can see it. So there's nothing special that needs to be done. Then, all right, so we use RCU assign pointer to atomically change a pointer. And the readers can now see it, the effect. And then what do? Then you call synchronize RCU and wait. So synchronize RCU will wait for all existing readers to leave their critical section. New readers can come in, that's fine. Okay, and they'll, of course, see the new pointer. But existing readers may or may not see this new pointer because they may have already gotten past the part of the critical section where they're reading. We don't know. So synchronized RCU will just wait. So what we're going to do, our code is going to look something like the following. Let's say we're replacing. So here's what we'll do. This is an example updater, which is going to modify the first node in a linked list. So we go ahead and allocate a new node. That's and then find old is going, and then we get the current version of head. Call that whole old. We're going to go ahead and then fill in P with the new value and key we want, and then read from old. So that's the read part. So we basically done a read and then a copy. So we are reading old, copying it into P, making the changes we want. So this will update the next pointer and the old. Up to this point, there's no problem because we're not seeing, the readers aren't seeing any of this. Now, atomically, we assign the pointer and change the head pointer. Right? So we did have something like this. What we've done is created a new object, put in its new values here, and then the RCU assign pointer goes ahead and updates head to point to here. So at this point now, after the RCU assign pointer, we have new readers that can go ahead and enter, and when they go ahead and call RCU dereference, they'll get the new value here. We have old readers who may have already gotten the value of head, and so we'll get the old first element of the list, or they may get the new element of the list, depending on where they are and whether they've done an RCU dereference or not. But in any case, the old pink value here continues to be valid. So whatever its old key and its old value are still accessible, and it can still traverse this next link here to get to the second element of the list. However, the updater needs to avoid a memory leak to free this old first item. When is it safe to do that? It's safe to do that when all of the readers that were in progress at the time we did this assign pointer have finished. And that's what the synchronized RCU is going to do. After that, we're guaranteed no one's looking at old, so we can go ahead and free it. So that's an example of the updater. One thing to note is that synchronized RCU is synchronous. That is, it just sits and waits. It is also possible to use a different API. So there also exists, and I'm not sure the name of it, but let's call it sync RCU callback. So what you do is you pass in a function here. So this might be a func that frees old. This is an asynchronous call. So synchronous RCU sits and waits, and then you just put the cleanup code afterwards. Sync RCU callback goes ahead and is asynchronous, and that'll return immediately. You do not have the free code after it. Instead, you put the free code in a function that will be called by the sync RCU callback when, again, all the readers have gone through. So what are our goals for RCU? What do we get out of this? Well, we get concurrent reads. So this is concurrent both with other readers, but also with updaters as well. What else do we have? We have low computation and space resources. So it's going to be cheap. And we also want to have a deterministic completion time for reads. So we don't want to, for instance, sit and have to wait for a lock to acquire a lock, because we don't know how long it can take to do that. How do we actually implement this? Well, let's look first at the readers. All right, so let's say we have a non-preemptive kernel. Okay, an example of that would be like JOS or like Linux 2.4, so earlier versions of Linux. So let's look at the implementation. So the implementation of, and here's my saying, right? My saying is, nothing is faster than nothing. So what are we going to do? We're going to go ahead, and this will become clear as we look at that. So the RCU ReadLock is defined to do nothing. RCU read unlock is defined to do nothing. How can this possibly be? We will look at this. It's a puzzlement. But certainly this is fast and it's deterministic, right? How long does it take to read a lock? To enter into your reader critical section? No time. How long does it take to leave? Also no time. What about dereference? So the dereference is a little more complicated. So the dereference does some C magic to basically make sure that we have a read barrier. So what the RCU dereference does is basically declares, defines a variable called __PL, which is the dereference of the ampersand of P, which seems like a no-op, but the key is it does a volatile. So the volatile keyword is part of what in C will provide a read or a write barrier. So the fact that we have a volatile variable here means that its value could be changing, and therefore its order doesn't change between other loads. So that takes care of the compiler not moving any loads before or after this, or across this. And then the read barrier depends will actually add a data dependency read barrier. Again, depending on the architecture, this may turn out to be nothing. Is this expensive? Not at all, right? This is effectively, so as far as the compiler is concerned, it doesn't really need to do any code for this other than to actually go ahead and dereference P. So how do these locks and unlocks work? So the nice part about really this is that the reading is just about as fast as we could possibly make it. We have to ensure that the compiler and the architecture have read barriers, and then we do nothing else. We couldn't ask for anything better than this. But how can this possibly work? Well, I guess the real difficult part must be in the updater. So let's go look at the updater. Right? How is it that synchronized RCU can work? So how does synchronized RCU work? Well, we don't know when we enter a reader critical section. We don't know when we exit a critical section. So when we call synchronized RCU, we have no idea how many reader critical sections we might be in, right? Well, that's not quite the case. So we know that the readers are not allowed to block in the critical section. Okay? They're not allowed to do any yield or anything else. They have to just run through. So therefore, if we have n CPUs, we actually know there can be at most n-1, we can be at most n-1 critical sections. So we do know that. We have at most n-1 readers in our critical section. And also what we know, so we know the readers aren't allowed to yield during their critical section. So what we can do then is, the converse of that really tells us if a yield happens, if a reader yields, we must not be in the critical section. Maybe what I really want to say is, if anything on the CPU yields, we must not be in a reader critical section. So here's the simple idea. If we call synchronized RCU on CPU 0, and every other CPU is called a scheduler since synchronize RCP was issued, then all the old readers must be done, because that means every other CPU has called yield since synchronize RCU was called. And if every other CPU has done it, that means we're not in a reader critical section. Okay. So let's make sure we're clear on this. What we're saying is we don't have any knowledge of which readers are in their critical section or not in their critical section, or how many of them there are. But we're using a side effect, right? We're using a hint that has been provided, and that hint or breadcrumb is that while we're in a critical section, so we're running along, and we are in a critical section from here to here, which no one else knows about, right? Because of the fact that we've notified no one in any way. But what we do know is that there are no yields in here. Okay? So no yields happen in here. Therefore, if we do a synchronized RCU at some particular point in time, so if we do a sync RCU here, then we know there are no yields here. If there is a yield at some point, so let's say here, we do a yield, we know after that we can't be in a reader critical section that was active at the time the sync RCU occurred. So the sync RCU happens on CPU 0. This is CPU 1. CPU 1 is going along. We're in a reader critical section. Right? Maybe the reader critical section started here. Maybe it started before, right? Could have been here. Could have been here. We don't actually know because we don't actually when it starts. But we do know that if a yield happens, we're not in the critical section. There might be a lot of time here that passes where we're not in the critical section and yet we haven't yielded yet. And sync RCU has to be conservative. So sync RCU doesn't know the edges of the critical section. All it knows is that after the critical section ends, at some point there's going to be a yield. And that's what it's looking for, the later yield. If it does this for every single CPU, then we know that after they've all yielded, we're out of all the critical sections. Maybe vastly overestimated, right, how much time we had to wait. But we do know that that's true. So that's what we're going to do. All right, so how is this going to work? How is synchronized RCU going to work? What we're going to do is we're going to keep some sort of an array of how many times the scheduler's been called for each CPU. So let's say we have 6 CPUs, and maybe this is 3, 352178, okay? And now let's say we call synchronized RCU. And let's say we run this on CPU 0. So in that case, here's what it's going to do. It's going to take a copy of this array. And it's going to wait until we get such that this is at least 6, and this is at least 3, and this is at least 1, 7, and 8. So we can basically just sit and wait until sketch count is greater than or equal to so 3 because we're on CPU 0. We don't need the scheduler to have run already, but make sure it's a run on 1, on 2, on 3, on 4, and on 5. And once that's true, then we're done. The asynchronous one can work just as well. So we make a call, we pass in a callback, and then it can sit and every so often be checking. And as soon as the schedule count is at least this big, it can go ahead and call the callback. There are a lot of tricks to sort of make this quicker. So actually what happens many times is we don't just wait for exactly one of these scheduled counts. We might only check every so often, and every so often just look and say, we've got this slew, let's say, of callbacks to call. that are now active because we have verified that we're no longer in reader side critical sections. There is some modification we have to make if we are using a preemptive kernel. If we're using a preemptive kernel, so an example of a preemptive kernel would be like XV6 or a recent Linux, then we need to make sure that when we're in our read side critical section that we don't actually get preempted. So we would actually define RCU ReadLock so that we, again, don't actually lock anything, but what we would do is current thread info arrow preempt count plus plus. So the preempt count, if it's non-zero, says you can't preempt this thread. And then conversely, we'll decrement the preempt count. So that'll just ensure that during this critical section we don't get preempted. And that is all we need for a critical section, right? A read side critical section, the rules are, again, we don't yield during it, and we agree to only access our RCU protected data structure from within this read lock, read unlock. And finally, really, that we actually use the dereference macro. What happens if you have multiple writers? Right, this takes care of multiple readers and one updater. If you have multiple writers, you still need to have some sort of a lock to prevent multiple simultaneous writers overwriting one another. So you'll do locks for that, but this is designed in a situation where we have a data structure where we have lots and lots and lots of multiple readers, and we're not so concerned about the number of multiple simultaneous writers. Some of the limitations, if you have something that can't be captured in a single atomic operation, so if we do our assignment of a pointer, we have to do something more than that, then we can't do that. So let's look at an example. So where does RCU not work? Well, if you've got data structures that have some update that can't be captured in a single atomic pointer update, you've got a problem. Singly linked list, we can deal with because we are atomically updating the head pointer or atomically updating some next pointer. Trees actually can work too, although you're going to end up copying much of the tree possibly. Right? So if you have a tree like this, then you may end up having to copy, let's say, parts of the tree until you get up to the root. So you will have, let's say, the old tree and then some, let's say, parts of the new tree, and you'll update the head atomically to point from the old to the new, exactly like ZFS. If you've got something like a doubly linked list, that is more of an issue. And then we also have backpointers. And the problem here is, let's say you want to modify the middle element. The problem is you need to atomically both change, so you make a new node, right, with new values in it. So far we're okay, right? This is before the reader can see anything. But now you need to somehow atomically change two pointers. Change this one and change that one. Not possible atomically. So normally doubly linked list wouldn't work. However, unless you wanted to somehow copy the whole list and just update the head, which seems extremely expensive. Linux actually still allows it. And the way it allows it is it has a rule that if you have an RCU reader, it's not allowed to use the back pointers. It can only use the forward pointers. So from its point of view, it is an atomic update. Since it's never looking at the back pointers, it doesn't matter whether they're updated correctly or not. Why would you want to have a doubly linked list if you're not going to use the back pointers? Any readers are not going to use back pointers? Well, the reason is, let's say you want to do, for instance, a delete. So you have a list to delete that takes a node pointer. If you have a singly linked list, then this node pointer is going to take you somewhere in the middle of the list. it's going to be an order n operation to find the previous node so that you can update it, right? So if I've got a linked list, singly linked list, and I decide this guy I want to delete, so I pass in a pointer to here and say delete this guy, I've got to go back to the head and walk through the list in order to find this guy, the previous guy of the one I want to delete, because that's his link I'm going to be able to update. If, on the other hand, we have, so it's an order n if singly linked. On the other hand, if we add backlinks, it suddenly becomes order 1, because from here I can in one step find my previous and then update its link, and in one step find the next and update its link. RCU was added to Linux in 2002 by Paul McKinney. And then what's interesting is he referenced this work in his 2004 PhD thesis. So definitely a case where the research actually made it into the real world. So now there are more than 10,000 uses in the kernel of RCU. It's especially used in the file system and networking. And we have to in cases, for instance, we have to synchronize millions of kernel objects, like let's say directory entries. The advantage of not having to lock when you're reading is extraordinary. Both the time that it takes and as well just the space, because if you had 4 bytes, that'd be 4 megabytes of kernel objects just for the locks themselves.